Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3. So today we are going to present about our mini project which is Heat Exchanger A. So this is my group members, Zarif, me, Fazlina, Nuriyandina and Aliasna. So this is our task delegation. So first I will start with the introduction of heat exchanger. So in a variety of industrial processes, agitated vessels are used to heat or cool liquid. Agitation is the process of giving a liquid bulk motion to igniting and diffusion. So basically agitation in a process usually result in physical change, chemical change or a fast rate of transport and it might happen all at once. Heat transfer is usually required for two purposes, raising and maintaining the temperature of the vessel content to reaction levels and lowering the temperature before the contents are discharged. So there are two ways for heat to be transferred. First is by jacket. In this process, the heating of cooling medium is made to flow through the channels so that better control of the flow distribution is achieved on the outside vessels. A jacket can be full convectional jacket, a dimple jacket or a limpet coil which is half bar jacket. A conventional jacket has the advantage of covering the entire wall and base surface and is very easy to put together. A dimple jacket allows light gauge metals to be used while maintaining strain. For high pressure on the service side, a half part jacket may be less expensive and has the advantage of spreading several service to different areas of the wall. So next is it transferred by coil. The most common design is full helical coil which allows the most surface area to be placed but required a two-piece vessel with rather expensive main flange. So a jacket has the advantage of having no extra materials of construction and no extra metal surface in contact with process other than typical vessel wall for extremely corrosive or highly reactive compounds. A coil has the advantage of providing wide surface area. But in this project, the process is undergoing an unsealed operation and we use the vessel that are fully insulated. In this project, we would like to evaluate whether the vessel with the following specification can be used to perform the heating requirement. The process is done by a heating tube inside the vessel is submerged inside the vessel. So I think that's all from me.
Next, in this section, we will talk about solution and calculation of heat exchanger problem given. The question given is, in a certain production plant, 1 meter cube of milk is to be heated from 25 to 70 degrees Celsius within 5 minutes in a highly agitated vessel. The heating is done by a heating tube inside the vessel that is submerged in the liquid milk. Hot water at 90 degrees Celsius are available at a flow rate of 2.4 kg per second and can be passed through the tube. You would like to evaluate whether the vessel with the following specification can be used to perform the heating requirement. Specification given is capacity equal to 4 meter cube, tank of tube is equal to 40 meter, diameter of tube equal to 50 millimeter, external convection coefficient provided by the manufacturer equal to 1000 watt per meter square Kelvin, neglect the resistance of the tube within wall, vessel is fully insulated. The question wants us to draw a schematic of the process, state the fluid properties that you use for the calculation, derive an expression from energy balance and heat transfer equation that can determine the mid temperature and the exit temperature of hot water as a function of time, state any assumption made, your recommendation on the suitability of the available vessel with the current heating stream, provide a plot of variation of heating time with the flow rate of hot water, how does flow rate affect the heating time? Discuss what are the possible factors that affect the external heat transfer coefficient. Discuss two possible ways that you can take to reduce the heating time other than flow rate.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurin Adina binti Abdul Aziz and my metric number is 200411. So today I will continue with the schematic diagram of the process. As being stated in the question, the process is happen in an agitated vessel. So this is an agitated vessel that we draw. So in the diagram, we can see a fully insulated tank full with 4 meter cube milk, and we can see an heating coil here and an agitator, or we call it as an impeller. And so in the question, it being stated that the milk here will be heated from 25 degrees Celsius to 70 degrees Celsius. So the heating will be done by an agitator. Next, we have a heating coil. The heating coil where a heating medium or cooling medium in and out. In this case, we can see we have hot water in at 90 degrees Celsius with flow rate of 2.4 kilogram per second. It will be heated in this vessel, pass through this vessel, and hot water out here. So DTH is unknown because it will be defined by the calculation later. This heated, you can see the black arrow here shows that the heat is transferred from the hot medium to the cold medium, as we already learned in law of thermodynamics. In this milk, we have the temperature which is TC. Also will be calculated in the calculation later. Next, we have fluid properties used for the calculation. First of all, we have properties of water at 90 degrees Celsius. We can find it from table A9. We get this of milk at 47.5 degrees Celsius. This is also we get from table A9. First of all, water and milk will be used in the calculation to find to answer the question that being asked. That will be us. That's all from us. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zarif Izzah bin Muhammad Zuzain. So I will continue the derivation part. Okay, first of all is the basic equation. We list out the energy balance equation and heat transfer equation, which is in equal to out m dot h cph th in minus th out equal to u as delta log in. And then heat transfer equation equal to in equal to accumulation. U A S delta T log min equal to MC CPC delta TC over DT. And then log min temperature delta T log min equal to delta T1 minus delta T2 over log delta T1 minus delta T2. Delta T1 is equal to the TH in minus TC and delta T2 equal to TH out minus TC. Okay, next from the equation 1, just now we see that MH CPH, we just change the delta T log min equal to TH in minus TH out as follow, and then we solve it as usual. Then we get the TH in minus TC over TH out minus TC equal to exponent UAS over M dot H CPH. And then proceed to the TH out minus TC, and then we get the TH out equal to TH in minus TC over exponent UAS M dot H CPH plus TC, which is we get the TH out in terms of TC. And then we let X equal to UAS over M dot H CPH, and we get a new equation, which is equation 3. TH out equal to TH in plus TC exponent X minus 1 over exponent X. Okay, next equation 3, we put equation 3 into equation 2, so we get as follow equation. Then we solve it as usual. We get the TH in bracket of exponent X minus 1 minus TC exponent X minus 1 equal to MC CPC X exponent X over UAS times delta TC over DT. And then we do the integration, which the limit is TC and 25, and on the other side is T and 0. So we just solve it as a normal integration until we get 1 over exponent X minus 1 non-TH in over minus TC in bracket TC over 35 equal to UAS MC TC X exponent X times T and bracket of T and 0. So we change the we fill up the limit into the equation, which is TC and 35 and T and 0. So we solve it as usual until we get the non-TH in minus TC over TH in minus 25 equal to UAS over MC CPC times UAS over M dot H CPH times 1 over exponent X minus 1 times 2. And then for the, after we solve it, we get the TCT, which is time equal to 19 minus 65 exponent M dot H CPH over MC CPC times 1 over exponent X minus 1 times 2. And then we are setting the TCT equation obtained into the equation 3. So we get the TH out T equal to TH in plus 90 minus 65 exponent M dot H CPH over MC CPC times 1 over exponent X minus 1 times T, and exponent X minus 1 over exponent X is the highlight equation below. So I think that's on my part. So the next part we cover by Uni.
So next, before we proceed with the integration described by Zarif earlier, we considered a few assumptions. So first is, since the vessels are fully insulated, the heat loss from the vessels can be ignored. Second, properties of fluid don't change during the process, hence the U coefficient assumed to be constant over all the heat exchange surface. Workflow in the control volume is neglected, only be considered when the fluid has large viscosity. Temperature milk, TC will be saved at any point of the vessel since this is a perfect mixing tank, which means that we use a continuous stirrer or reactor. Next is the thermal resistant tube is neglected due to its low value because of the thin wall. And last, the dish bottom of the vessel is ignored and the vessel assumed to have a flat bottom. I think that's all from us. Next part will be continue with Alia Husna.
Assalamualaikum warahmatullahi wabarakatuh. My name is Alamsna Piditsari and my tag number is 201737. I present the application 5, which is the recommendation on the suitability of the available vessel with the current heating stream. To prove the suitability, we need to do some calculation. So based on the properties of which stated earlier, we can calculate some value. First, surface area. To know the surface area, use formula pi dl, which is d for the diameter and l for length. So to substitute the value, we get the value for surface area is 6.283 meters square. Next, for the Reynolds numbers. We need to calculate the Reynolds numbers to know which type of flow, the hot water, to know the flow of hot water, the type of flow for the hot water. So after we substitute the value for the RE, we get the value larger than the 10,000. So the test of flow is 3 billion flow. Next, Nusselt number. We need to know the Nusselt number to get the internal convection coefficient. So the Nusselt number value, after we know the test of the flow, which is turbulent, use the formula 0.023 RE power of 0.8 times PR power of 0.4. So after we substitute the value, we get the Nusselt number 511.57. Next, the internal convection coefficient, HI. HI formula is nu K over T. K is the thermal conductivity and it is diameter. So from the Nusselt number value we get earlier, we can substitute the value here and get the value of HI, which is 6,906.165 watt over m square K. So after that, we can get the value of overall convection coefficient. The value of the overall convection coefficient U using formula 1 over 1 of H1 plus 1 of HO is 873.52 watt over m square K. And based on the results of derivation from the question 3, you can do the calculation for TC and TH after 5 minutes. So for the calculation for TC after 5 minutes, we let the X be equal to UAS over flow rate times by heat capacity of hot water, and we substitute the value and get the let X equal to 0.544. And then we need to find the exponent for the X. So the exponent of the X is 1.723. So from the exponent X value, we can substitute in the equation to find the TC after 5 minutes. So for the derivation, for the equation, substitute the value and we get the value for TC after 5 minutes is 70.99 degrees Celsius. Next, for the TH after 5 minutes, so this is the equation get from the derivation, that's for the X, and then we take the value at 81.65 degrees Celsius. So from the results shown above, the outlet temperature of hot water TH decreases from 90 degrees Celsius to 81.65 degrees Celsius, while the temperature of milk TC is increases. So the area of the surface is larger than the value of milk. So the vessel is suitable and large enough for the heating stream. Then the value of U, overall heat transfer coefficient, is 873.52 watt over m square Q. The value is quite high, so when the coefficient is high, it will result in faster heat transfer from the hot water to the milk. Thus, the milk temperature can be increased in a short time, which is 5 minutes. So, we can conclude that the available vessel is suitable for the current heating stream. So, next question 6, flow operation of heating time with the flow rate of hot water. So, this is a graph for the heating time versus mass flow rate of hot water. So, how mass flow rate can affect the heating time? Mass flow rate is directly proportional to the rate of heat transfer. An increase in flow rate causes an increase in the rate of heat transfer. When the rate of heat transfer increases, the heating time will decrease. This graph shows that an increase in flow rate causes decreases in heating time due to an increases in the rate of heat transfer.
All heat transfer in gyres take place in the form of convection and conduction. The milk is heated indirectly by using heat exchanger. The possible factors that might affect the external heat transfer coefficient are physical-chemical properties of fluid such as viscosity, specific heat, and thermoconductivity. Other factors are the type of fluid flow, either in parallel flow, contour flow, or cross flow. The external heat transfer coefficient also will vary depending on flow rates. The length and area of the heat exchanger also can be the factor because we can neglect the thermal resistance of the tube if the wall thickness is too small and the thermal conductivity of the tube material is high. In this case, we can say that the inner and outer surfaces of the tube are almost equal. We can reduce the heating time by using tube material that has high thermal conductivity. The higher the thermal conductivity, the higher the rate of heat transfer, thus the heating time will be faster. Next, the factor that can reduce the heating time is by increasing the surface area because it will absorb more heat. The increased diameter size of the tube will be affecting the area. The larger the surface area, the heat transfer rate also increases as the heat transfer rate is directly proportional to the surface area through the tubes.
So I will continue with the last part of our presentation, which is conclusion and reference. So firstly, we can conclude that available vessel is suitable for the current heating stream with the surface area of both vessel is 6.283 meters square and the overall heat transfer coefficient is 873.52. Next, we are able to find the possible factors that might affect the specific heat and thermal conductivity as being discussed in the discussion. Next, based on the graph that is shown in figure 2, we can see that the flow rate is decreasing with the increasing of time. Fourth, we are able to determine the ways of reducing the heating time by increasing the surface area and increasing the diameter size of the tube. Last but not least, we are able to get the melt temperature Tc equal to 70.99 degrees Celsius and hot water TH out equal to 81.65 degrees Celsius within 5 minutes. This is the result here is calculated by substituting the calculated area of surface, Reynolds number, Nusselt number, internal convection coefficient, overall convection coefficient into the derived equation that we already derived. That's all from our group. Thank you very much.